In lesson 4, we have proven that the only information that is required in order to completely determine a linear map is its action on the vectors of a basis of its domain vector space. In particular, at page 45, we have highlighted two practical methods to find a unique linear map F corresponding to the set of transformed basis vectors f of v1, f of vn. Since the action of f is determined by these vectors, we expect that also the properties of f depend on the vectors f of v1, f of vn. We start this lesson at page 48 by showing that this is exactly what happens. So we are at page 48, and let's consider this theorem. Let f from vector space V to vector space W be a linear map, and let B given by vectors v1, vn be a basis for V. Then we have that f is one-to-one if and only if f of v1, f of vn are linearly independent vectors in W. F is onto if and only if the family f of v1, f of vn generates W. Finally, f is an isomorphism if and only if f of v1, f of vn is a basis for W. The proof of the first statement requires a little bit of time. The proof of the second statement is very easy, and the proof of the third statement is a direct consequence of 1 and 2. So we start the proof of the theorem by point 2. To prove the second statement, we just need to recall two results that we have already proven. The first is that f is onto if and only if the image of f coincides with the vector space W. The second result is the statement of this theorem here, which says that if B v1 vn is a basis for V, then the family f of v1 f of vn is a family of generators for the image of f. By mixing these two results, we clearly have that f is onto if and only if the family f of v1 f of vn is a family of generators for the whole W. If we now assume statement 1, that is f is one-to-one if and only if f of v1 f of vn is a family of linearly independent vectors, then we can immediately prove statement 3. In fact, f is an isomorphism if it is simultaneously one-to-one and onto. But, thanks to statement 1, f is one-to-one if and only if these vectors here are linearly independent, and thanks to statement 2, f is onto if and only if these vectors here are generators for W. Hence, f is simultaneously one-to-one and onto, that is, f is an isomorphism, if and only if these vectors are linearly independent and they generate W, that is, if and only if this is a basis for W. Let's now see how we can prove statement 1. Let's start by proving the direct implication. That is, let's suppose that f is one-to-one, then we must show that this family here is free in W. First of all, recall that f is one-to-one if and only if its kernel is reduced to the only null vector of V. We're going to use this property in just a minute. In order to check if these vectors are linearly independent, we must write a generic linear combination of them with coefficients lambda 1, lambda n, and set it equal to the null vector of W. If this equality implies that all the coefficients are 0, then these vectors are linearly independent. Here I simply rewrote this equation in a compact form, and then I use the linearity of f in order to put out f from the linear combination and write f of this linear combination equal to the null vector of W. Now notice that since this vector here is nullified by the action of f because it's transformed into the null vector of W, this means that this vector belongs to the kernel of f. However, as I told you before, under the hypothesis that f is one-to-one, the kernel of f is just the null vector of V. So we have that this vector here is equal to the null vector of V, as it is written here. However, remember that V1, Vn constitute a basis for V, and so in particular they are linearly independent, which means that a generic linear combination of them is equal to the null vector of V if and only if all the scalars lambda j are zero. But remember that proving that all the coefficients lambda j are zero is exactly what we wanted in order to prove that f of v1, f of vn is a free family in W. Hence, the direct implication is proven. Let's now pass to the proof of the inverse implication. That is, now we are supposing that f of v1, f of vn is a free family in W, we must show that f is one-to-one. That is, that the kernel of f is reduced to the null vector of V. In order to do that, we consider a vector V that belongs to the kernel of f, and we expand V on the basis B. Then we apply f to this vector, and since this vector belongs to the kernel of f, f of V will give exactly the null vector of W. However, since f is linear, we also have that f of V decomposed on the basis B gives rise to this expression here. Now we just fix our attention on this part that remains of the equality. Since f of v1, f of vn is a family of linearly independent vectors, we have that this linear combination can give rise to the null vector if and only if every coefficient lambda j is zero. So if we introduce this information into the decomposition of V over the basis B, we have that V is equal to the sum of 0 times Vj for all j that goes from 1 to n. And so, since we are summing n times the null vector of V, of course we obtain that V is the null vector of V. And so, since V was the vector that we have considered belonging to the kernel of f, we have that the kernel of f has just the null vector in it, and so f is one-to-one. I wanted to discuss this proof because it contains a lot of results and techniques that you should be familiar with at this point of the course. If you had problems following the explanation or reading the proof on the notes, it is important that you go back and study again the concepts of linear independence, kernel, and image of a linear map. We have already recalled the fact that when we have a linear map F between vector spaces V and W, then its definition is completely characterized by how F acts on the vectors of a basis of V, say V1, Vn, and so by these vectors here. It turns out that not only the definition of F is characterized by these vectors here, but also its properties. In fact, F is one-to-one if and only if this family of vectors is free in W. F is onto if and only if these vectors are generators for W. And finally, F is an isomorphism if and only if these vectors form a basis of W. As an important consequence, this implies that a linear map transforms a basis into another basis if and only if it is an isomorphism. Let's now see a nice application that shows the usefulness of the theorem that we have just proven. Recall that in this example here, we have analyzed the endomorphism phi and psi whose expressions are recalled here and here respectively. As you can see, the expressions are quite different. However, remember that phi was built by associating the vectors of the canonical basis of R3 to the vectors W1, W2, and W3 that are recalled here. Similarly, psi was defined by associating to the vectors of the basis that is recalled here the same vectors W1, W2, W3 that was used in order to define the endomorphism phi. The situation is summarized here. That is, phi and psi were constructed by sending the vectors of two different bases of R3 to the same set of vectors. Thanks to the previous theorem, it follows that phi and psi have exactly the same properties, because these ones depend on the fact that the vectors w1, w2, and w3 are linearly independent or not, or a family of generators for R3 or not. So we don't have to repeat twice the analysis for phi and psi. As you can imagine, this becomes a very, very useful property if instead of having just two linear maps, we have a whole bunch of them. So let's check, for example, if the three vectors w1, w2, w3 are linearly independent. As usual, we know that we must write the generic linear combination of them and set it to the zero vector. We obtain, by performing the computations, this vector equation here that corresponds to this system of linear equations. By solving the system as it is written here, we find that actually all the coefficients a, b, and c are zero. So the three vectors w1, w2, w3 are linearly independent. This implies that both phi and psi are one-to-one maps. In fact, they both send the vectors of a basis of R3 into a set of linearly independent vectors. To finish the analysis of phi and psi, we can use this theorem here, which says that for an endomorphism, the fact of being one-to-one implies that it is also onto, and so it is also an endomorphism. For this reason, both phi and psi are two endomorphisms of R3. Let me stress again the fact that, without knowing that phi and psi were defined like this, we would have needed to check their properties separately using their different expressions written here. So, sometimes it is even more useful to know just the action of a linear map on the vectors of a basis than its explicit expression. We're going to end this section with an immediate consequence of the previous theorem. Let F be a linear map from the vector space V to the vector space W. If the dimension of V is strictly inferior than the dimension of W, then F cannot be onto. Before discussing the proof, let me give you an example. Imagine to consider a linear map F between Rm and Rn, with m strictly inferior than n. This map, for what we have just said, cannot be onto. Pay attention to the fact that we can say this just because F is a linear map. If F is not a linear map, what we have just said is not true. The proof of the theorem is very easy. In fact, by the second statement of the previous theorem, we have that F is onto if and only if the images of the vectors of a basis of V form a family of generators for W. However, we know that in a basis of V, we have a number of vectors that is exactly equal to the dimension of V. So the number of these image vectors will exactly be dimension of V. But since the dimension of V is supposed to be strictly inferior than the dimension of W, we simply don't have enough vectors to generate W, because in order to generate W, we know that we must have a number of vectors that is the dimension of W. Let me warn you again, if you had problems following the arguments of this proof, it means that you either forgot or didn't understand very well the concepts of dimension, basis, and family of generators. In this case, there's no problem. You have been exposed to several new concepts and it's totally normal to have doubts. However, before continuing watching the video, I invite you to go back to those concepts and clear your ideas. This section is one of the most important of the entire course. We're going to see how we can associate a hugely important object of linear algebra called matrix to a linear map. As always, we consider two vector spaces V and W over the same vector field F with dimension n and m respectively, and we fix a basis BV with vectors V1, Vn of the vector space V. As we have seen in the previous section, we can uniquely determine the action of a linear map F between V and W if we know how F acts on the vectors of the basis BV. So imagine that the images of the basis vectors by F are known. These images belong to the vector space W, and we can wonder what happens if we fix also another basis, this time of W. This basis here with vectors W1, Wm. Well, we have learned that whenever we have at disposal a basis, the most natural thing that we can do is to decompose a vector over this basis. In our case, we are interested in these vectors here, so let's write these expansions starting with the first two in order to see what happens. I have written the coefficients of the decomposition of f of v1 with a and the coefficients of the decomposition of f of v2 with b. However, it is easy to recognize that this choice is not very wise. In fact, if n is larger than 26, which is the number of letters in the Latin alphabet, at some point I will have to use letters from another alphabet, and this of course will create a chaotic notation. But now imagine that n is so large that we run out of all the alphabets that exist. In this case, we must invent new symbols, but you understand that this is not an intelligent strategy. A much wiser choice is to replace the notation of the coefficients in such a way that it remains coherent and it never runs out. For this purpose, mathematicians had the great idea to fix a letter, for example A, and attach to it not one but two indices. You can see what happens with this choice if you compare this notation here with this notation here. In this notation here, you have that 1 is associated with A and 2 is associated with B. Instead, in this notation here, 1 is associated with the second index 1 and 2 is associated to the second index 2. So this notation is much more coherent and it can never run out. Let's now consider the expansion of the generic jth vector f of vj. Coherently with what I said before, you can see that the index j that labels the vector v appears as the second index of the coefficient a. The index j runs over 1 to n because n is exactly the dimension of v, and we have exactly n vectors in a basis of the vector space B. Instead, notice that we have to perform the linear combination with respect to the vectors of the basis of W. W has dimension m, and so the index I, which is the first one that is attached to the coefficient a, runs from 1 to m. We are now going to see that the ensemble of all the coefficients aij, as the indices I and j vary, can be arranged in a tabular array called matrix. The explicit expression of the matrix is this one. The coefficients appearing in the matrix are also called the entries of the matrix. Before describing in detail the matrix, let me just tell you that the compact notation used to represent the matrix is this one here. As you can see here, the matrix A can be interpreted as being composed by rows or by columns. In general, a matrix has a different number of rows and columns, and when we interpret them as vectors, they belong to different vector spaces. In fact, as you can see from the explicit expression of the matrix and also from this compact notation in terms of rows, the matrix A has m rows. M, remember, is the dimension of the codomain of the function f, and the row vectors are elements of Fn. Instead, looking again at the explicit expression of the matrix A or to its compact notation in terms of columns, we see that A has exactly n columns, which, interpreted as vectors, are elements of Fm. The jth column of the matrix A has a very important meaning. In fact, you can see that the coefficients belonging to this column are exactly those appearing in the linear expansion of f of Vj on the basis Bw. From this remark, we gather the practical method to associate a matrix to a linear map. First of all, you have to fix a basis Bv of V and Bw of W. Then you have to apply f to all the vectors of the basis Bv, obtaining n vectors of W given by f of V1, f of Vn. Then you have to expand all these vectors as linear combinations of vectors of the basis Bw. Finally, you have to place the coefficient of the jth linear combination in the jth column of the matrix. The uniqueness of the association follows immediately from the uniqueness of these coefficients. If we want to be super precise, we must use this symbol here to denote the matrix associated to the linear map F with respect to the bases BV and BW. However, when there is no confusion, we will use this symbol here. The matrix A is far more important than being just a nice ordered arrangement of the coefficients Aij. In fact, in the next lessons, we're going to see that all the properties of F can be much more easily examined using A. And in chapter 3, we will show that matrices play a crucial role in the solution of systems of linear equations. Furthermore, matrices allow us to represent in an algebraic way geometric transformations as, for example, rotations, something that you'll study in the course of Euclidean spaces. So you see that there are plenty of reasons to study matrices. But for the moment, what we have to do is to discuss examples in which we put the practical method to associate a matrix to a linear map in action. Let's consider this linear map F from R3 to R2. F maps the generic vector of R3 written as xyz to the vector of R2 with the components x plus y and x minus z respectively. Notice that independently of the basis of R3 and R2 that we will fix, the matrix A associated to the linear map F will have 3 columns and 2 rows. However, of course, the entries of the matrix will depend on the choice of the basis. This is the first example of association between a linear map and a matrix, and so for simplicity, we consider the canonical basis C3 of R3 and the canonical basis C2 of R2. Following the practical method that we have just discussed, the first thing that we have to do is to apply f to the vectors of the canonical basis C3. So we write f of 1, 0, 0, f of 0, 1, 1, and f of 0, 0, 1. Then, in order to find the images of the basis vectors of C3, we just replace the generic components x, y, z that are written here by the components of the vectors of the canonical basis. We find these expressions here, and by performing the computations, we find the vectors 1, 1, 1, 0, and 0, minus 1. Now the next thing that we should do is to express the vectors that we have just found as a linear combination of the basis vectors of C2 and then place the components of these linear combinations on the columns of A. However, in this example, we have a great simplification because we have chosen the canonical basis C2 of R2. In fact, in this case, the components of these linear combinations are simply the components that appear in the expression of these vectors here. We have already seen that this is true and that this is a special property that is satisfied only by the canonical basis. If you want an example to convince yourself, pick, for example, the third vector that we have determined and write it as a linear combination of the two basis vectors of the canonical basis of R2. As you can see, the components are 0 and minus 1, but these are exactly the components of the initial vector, and so this linear combination is redundant. So, to conclude, the matrix associated to the linear map F with respect to the canonical basis of R3 and R2 is this one. In fact, the first column of A coincides with this vector, the second column of A coincides with this vector, and the third column of A coincides with this vector here. Let's now pass to this very similar example here. Let's consider the linear map between R3 and R3 that we have already examined in this example here. The expression of the linear map was the following, and since we are dealing with R3 and R3, we know that the matrix associated to this linear map, independently of the choice of the basis, will be a 3 by 3 matrix. In order to remain as simple as possible, let's fix also in this example the canonical basis of R3 for both the vector space domain and the vector space codomain. In order to find the matrix associated to F with respect to the canonical basis, we have to transform the basis vectors of the canonical basis of R3, which are these ones here, and if we replace x, y, and z by the coordinates of the three canonical vectors, we find these vectors here. Now, thanks to the same argument that we have used in the previous example, since we have fixed the canonical basis in R3 interpreted as vector space codomain, we have that the matrix A associated to the linear map F will have the three vectors W1, W2, and W3 as columns. As a consequence, the matrix associated to F with respect to the canonical basis both in the domain and codomain vector space will be this one here. The important take-home message of these two examples is the following. If the codomain vector space W of a linear map is Fn and its basis is the canonical one, then we can avoid the last step of the practical method discussed in the previous page and use immediately the basis vectors of V transformed by F as columns for the matrix A. However, pay attention, this is not true if W is not Fn and if BW is not the canonical basis. Okay, these two examples allowed us to warm up. Now let's move on to more complex cases. In this example here, we have analyzed this linear map, which was defined by transforming the vectors of this basis of R3 into the same vectors W1, W2, and W3 that we have examined in the previous example. Thanks to the previous considerations, we have that the matrix associated to G with respect to the choice of the basis BV and the canonical basis of R3 is the matrix whose columns are the vectors W1, W2, and W3. As you can see, this matrix coincides with the matrix associated to the linear map F that we have discussed before. Here it is. So you can see that the two matrices are equal. However, we have said that the association between a linear map and a matrix is unique. So how is it possible that two different linear maps, G that you can see here and F that I reported here, have the same associated matrix? Well, the answer, of course, relies on the fact that the association between a linear map and a matrix is subject to the choice of two bases, one in the domain vector space and the other in the range vector space. If we examine closer the choice of the basis for f and g, we see a difference. In fact, as you can see, the canonical basis was our choice for the range vector space for both f and g. However, the canonical space was the choice of the basis for the domain vector space of f, but BV, which is different than the canonical basis, was the choice of the basis for the linear map G. To conclude, this nice example shows us that if we don't choose the same basis for both the domain vector space and the range vector space of two different linear maps, we can end up having exactly the same matrix. However, if we replace the basis BV with the canonical basis, then we must end up with two matrices which are different because F and G are different and we have fixed exactly the same basis for both the domain and the range vector spaces. Let's verify this. As we know, in order to do that, we must go back to the explicit expression of the linear map G, which is written here. And then we have to replace the generic expression of xyz by the expression of the canonical basis vectors that are written here. Following the rules specified by the function g, we obtain these new vectors, which will become the columns of the matrix A associated to G with respect to the canonical basis for both the domain and the range. This allows us to verify what we have expected, but also to show that if we consider just one linear map G in this case, and we change the choice of a basis either in the domain or in the codomain, in this case, of course, we have changed the basis in the domain vector space, then we end up with two different associated matrices, this one here and this one here. I think that now, with all these examples, the importance of the choice of the basis for the domain and range vector space when we associate a matrix to a linear map has become clear. Finally, let's pass to the last example, this one. We fix again our attention on the linear map G, but this time we fix the basis BV also for the range vector space, and for the sake of simplicity, we simply denote the two bases with B. So what we want to do is to find the matrix A associated with G with respect to the basis B for the domain and for the range vector space. From the previous example, we know that G transforms the vectors of the basis B into the vectors W1, W2, and W3 that are written here. However, we can't use these vectors as column for this matrix, because now, as I told you before, we have chosen this basis B here, which is not the canonical basis, as the basis for the range vector space. So what we need to do is to expand these vectors over the vectors of the basis B and place the coefficients of the expansions into the columns of this matrix here. Let's start with W1. So we write W1 as the linear combination of the three vectors belonging to the basis B, and the coefficients I have already written are those that will appear in the first column of this matrix. If you perform the computations, you arrive to this vector here, and so you have a vector equation, and you can identify the first component, the one written in red, the second component written in green, and the third component written in blue in order to arrive to this system of linear equations, this one here. If you follow the system as I indicated here, you find a unique solution that will give you the elements of the first column C1 of the matrix ABB of G. If you want to obtain the columns C2 and C3, you have to expand the vector W2 and the vector W3 as a linear combination of the basis vectors with the coefficients that will appear in column 2 and column 3. Again, you do that by performing the computations that are written here and here, obtaining the corresponding vectors, and solving this vector equation here by transforming it into a linear system, and the same for this vector equation here. As a very, very useful exercise, you can check that with this strategy you arrive to this column 2 here and this column 3 here. Let's recap what we have done in the examples that we have just discussed. By choosing three different combinations of bases for the range and domain vector space of the same linear map G, we have found three different matrices associated to the same linear map. In chapter 3, we're going to see that it's highly desirable to work with a matrix that has as many zero entries as possible. And so the most desirable matrix associated with G among these three ones is this one. In fact, we have 3 zero entries here. Here we have no zero entries, and here we have just 1 zero entry. However, notice that the most desirable matrix is not the one corresponding to the choice of the canonical basis in both the domain and the range vector space. This shows that even if the canonical basis is the easiest one to deal with computationally, it is not necessarily the one that leads to the most desirable matrix associated with a linear map. Keep this in mind very, very well, because it will be fundamental when you study the eigenvalues and eigenvectors of matrices. We conclude our set of examples by reversing the direction, in the sense that we're going to show that given any matrix, two vector spaces and the choice of a basis for each of them, we can uniquely recover the linear map associated to this matrix. Let's start, of course, with the easiest scenario. We have this matrix here, and we want to find the linear map F from R3 to R3 such that this is the matrix associated with F with respect to the choice of the canonical basis for both the domain and range vector space. Thanks to the choice of the canonical basis, we know that this task is very easy. In fact, each column of A will simply be the image vector of every vector of the canonical basis of R3. And so we have that f of the first vector of the canonical basis of R3 will be 1, 0, 1, taken from this column. F of the second vector of the canonical basis will be 1, 1, 0, and f of the third canonical vector will be 2, 0, 3, right here. Since we know how the linear map F acts on the vectors of a basis, we know everything about the linear map, right? Because we can extend it with the practical method that we have already seen in action. We take the generic vector v belonging to R3 written as xyz, and we decompose this vector on the canonical basis like this, and then we apply f to this vector, which means by linearity that we have x times f applied to the first element of the canonical basis, plus y times f applied to the second element of the canonical basis, plus z times f applied to the third element of the canonical basis. If we replace these vectors here by what we have just found, we arrive to this f of x, y, and z equals to x times this vector plus y times this vector plus z times this vector. We perform the computation and we find the final generic expression of the linear map f, this one here. By putting the expression of f and a side by side, you can find the pattern that allows you to immediately express a matrix as a linear map with respect to the canonical basis of both the domain and the range vector space. Think about that, and then we'll discuss it during our weekly meeting. At this point, you can ask, but what happens if we don't fix the canonical basis either in the domain or range vector space? Well, let's see what happens by choosing, for example, the basis B of the previous examples. In this case, you have to remember precisely the definition of matrix associated to a linear map. The entries of the first column of A, in this case, will be composed by the coefficients of the expansion over the basis B of the vector f of 1, 1, 1. Why that? Because this is the first vector of the basis B, as I recall here. Similarly, the elements of the second column of A will be the coefficients appearing in the decomposition over the basis B of the vector f applied to 3, 0, minus 1, which is the second vector of the basis B. Finally, the entries of the third column of A will be the coefficients of the expansion over the basis B of the vectors f of minus 1, 1, and minus 1, which is the third vector of the basis B. Now notice that you have three computations, this one, and this one, that you can easily perform, and you obtain these three vectors, which are nothing but the images by f of the basis vectors of B. So you have explicitly found out how f transforms the vectors of the basis B, which, as you know, is enough to recover the explicit expression of f. The first thing to do is to express the generic vector xyz as a linear combination of the basis vectors of B, which, however, is something that we have already done in this formula here. So we can avoid repeating the computation and we find this expression. Then you apply f to both sides of this equality here, and you use the linearity of f, and so you end up with this expression. Finally, you replace these vectors here by the vectors that you have already explicitly found here. You perform the computation and you arrive to the explicit expression of the linear map F.
One of the key concepts that you have to recall from this course of linear algebra is how to associate a matrix in a unique way to a linear map between vector spaces once you establish two bases of these vector spaces. The steps in order to do that are the following. First of all, apply f to all the vectors of the basis of V. Then expand every image on the basis vectors of W like this. Finally, build the jth column of the matrix by using these coefficients here, that is A1j, AMJ. Letting j run from 1 to n, you have all the columns of the matrix uniquely associated to the linear map F through the bases BV and BW. Notice that with this construction you end up having m row vectors for the matrix belonging to Fn and n column vectors for the matrix belonging to Fm.